so it's 4:15, and I think I'm going to get started, even though there's a fair number of people still milling in the hallways, just because I probably made too many slides. So 1 or 2 minutes, and I'll get started. All right, cool. All right, well, hi, I'm Sterling, everyone, and I'm here to talk about Apache MyNewt, which is probably the smallest of the operating system efforts that have been presented today. But I'll give you a little bit of an overview of our project. Very similar to both Zephyr and Mbed, we're an operating system that's targeting Cortex-M and kind of that class of processors. So we are agnostic of MCU architecture. We want to work on Intel, we want to work on MIPS, but if you kind of think about the applicable space for our operating system, it's really Cortex-Ms, and that's where we've spent a lot of our early time. So anywhere from an M0 to an M7 is really our target architecture. And kind of during the talk, I'll just talk a little bit about what the motivations behind Apache MyNewt were, why we decided to start yet another operating system effort, and kind of what our philosophy behind it is, right? Because I think all of the operating systems up here today really do kind of have good end goals, but maybe different things that they're optimizing for. So I'll talk a little bit about what Apache MyNewt is really focused on getting right first, recognizing that we all have kind of expansive roadmaps towards the end of it all. So my background is was from a company called Silver Spring Networks. At Silver Spring Networks, we did networked power meters, networked street lights, and kind of some of the first smart city networks. So we deployed 23 million IPv6 connected devices, and it was my job to manage the firmware team that developed the software that ran on those devices, but then also ran upgrades of those devices on customer networks. So we had service level agreements where when we upgraded devices, we couldn't brick them. We had devices that lived in the field for 10 to 15 years, where we would constantly have to provide software updates to those devices, and we had 50, 60 different revisions of hardware and manufacturing options and all of those things out in the field. While we couldn't go and brick 23 million devices, yet we still had to release software to run on those devices. And so Silver Spring was, this work was done in 2004. Right? And at that time, there wasn't a lot of uniformity in the space, both on the hardware side. So if you looked at the chipsets we used, it was an Atmega 128 that we put a full IP stack on and a full mesh networking stack. External radios, we had 2.4 and 900, so we had 2 radios. We had an external flash chip, an external RAM chip eventually. And so the board was a whole bunch of chips that weren't really coordinated in any fashion. And as time went by, Silver Spring's hardware architecture evolved and things got more integrated and smaller. And like you see today, there's a whole bunch of system on chips. The new TI chip, as an example, has a 802.15.4 radio in sub-gigahertz and in 2.4, and Bluetooth, all in a single chip design with a processor with memory and flash to run an operating system. So we saw hardware getting a lot more integrated in these endpoints. But we had kind of built our own operating system stack as a company, right? So when we started out, we used UCOS from Micrium, and we modified it because the scheduler was a big array, and we wanted to have a sleep list and a run list. We built our own memory debugging interfaces. We built our own bootloaders, our own flash file system. We built everything that you would typically think of if you thought of Linux and an operating system that didn't really exist in the space we were targeting. And so, of course, we did that on a very tight time schedule, and our boss didn't care about the beauty of it. What was the first thing you get rid of? It's security, right? And so we had this very rudimentary operating system that over time we evolved, and we had to live with the mistakes we made in developing that operating system for a very long time, right? Once you've written the right protect area of Flash, it's really hard to drop compatibility for something if you've messed the format up. And so there were all of this kind of pain that we built. And it's a little bit like, you build this house of cards because you have to build a connected lock or a connected wearable or some sort of connected product, but you then have to build the entire stack up yourself, and then you have to scale that. and you have a massive amount of resources spent in scaling operating system functionality, which isn't really your core expertise as a product company. And we certainly found at Silver Spring, I mean, I think it was a team eventually of 15, 20 people just on the core infrastructure. Even with that resource spend, our compilers were years out of date. We found a bug in this one compiler, and it worked, and we forgot what the bug was that we found, so we were deathly afraid of upgrading in case we ran into it. And there were all these things where you just had a very old tool chain because it wasn't really our core expertise to maintain that tool chain. And really, that's what open source is really good at, right? Having these platform technologies that cut across things and actually outsourcing the maintenance to a broader community of people who share the same problems that you have. So Apache MyNewt is a preemptive real-time operating system for Cortex-M environments, but it's really about providing the whole stack for somebody to develop a product. So this means at the base level, it comes with a bootloader. That bootloader works on all of the on all of the hardware platforms that we support. It has support for security. So all images that are uploaded to the device are signed SHA-256 within either RSA or ECC DSA in the bootloader. We've also gone to the point of on the chips we support the various options for linking these images. So on higher end host processors, we dual bank images. On the lower end processors like a Nordic, we'll actually support in-place upgrade where we separate the operating system and kernel and we upgrade them in sequence. A flash file system, so multiple flash access mechanisms. As you know, on these kind of small platforms, a file system sometimes takes up way too much memory. So we have things like flash configuration variables, circular buffers that allow you to write data to flash in a standard format, but we handle things like CRCing and encrypting that data and tying that into our configuration system. So kind of the base level, we've built that secure bootloader flash file system. On top of that, we have the OS and the hardware abstraction layer. So the OS is a standard preemptive multitasking RTOS. There is literally no magic in it. But when we looked at to build something, what we saw was, it's not that hard to build a real-time kernel. It's actually, I think we spent 2 weeks on it, maybe 3 in terms of testing. But what you miss in a lot of the kernels that are out there is, or at least a lot of the open source kernels, is support for debuggability and support for things like unified buffer schemes. So a lot of what we did was tie together debugging interfaces into our own kernel. So we have stack guard and stack checking. We have all of our memory pools actually count, freeze, and allocs. We've built a sanity task that ties into the watchdog and keeps the operating system up. So it's really been about focusing on making the kernel very, very easy to debug and tying into the rest of our system. There's a hardware abstraction layer, so we've done kind of a dual approach here where for every MCU we support the HAL. The HAL is base processor level features, so SPI, I2C, UART, all of those things. The HAL runs completely independent to the operating system itself. So you can put the HAL in the bootloader as an example. And so if you add serial boot support, you can still leverage the HAL without requiring the operating system. And it's really targeted at just the things that are common across MCUs. So we don't bother with, for example, ADCs. We don't, they're really, really complicated, and they're really specific to MCU vendor. On top of the HAL, what we've done is layered a drivers infrastructure. So for kind of standard things, you can use the HAL. So if you're talking to flash chips, for example, that's a driver that then talks through the HAL SPI interface, or could talk natively to the processor or any other number of interfaces. So we have a drivers interface on top of that. That's where we tie in all of our power management. So it's a tickless RTOS with sleep support on top of that. Stats and logging infrastructure is kind of one of the most unloved things we've seen in the kernels out there, and actually one of the most important things, right? So we've spent a lot of time really focusing on, if you have a product out there, how can you go and how can you debug that product? Right? How can you, at scale, see issues that are in the field? We've had issues in previous lifetimes of products that, for example, the radio performance was worse on a specific version of that product because traces weren't buried low enough when talking to the flash. And so radio performance was 20 dB less just on the specific SKU of the specific manufacturing product and only when we read from flash. And that had a large impact on network performance. If you don't have those statistics and that logging throughout your code, and that isn't done in a way that's code and memory efficient and configurable, it allows you to not count certain statistics or to compile out statistic names even with production images. If you don't have that inherent, then it's really hard to debug these products out in the field. And then it's kind of console shell, config and upgrade. And then where we really kind of tie in again to providing something that's differentiated is in the networking stacks themselves. And specifically, our focus and our expertise is in the wireless networking stacks. So we think, there's a lot of work that needs to be done to improve embedded IP stacks, as an example. And we're going to probably just glide on other people's work there. We integrate LWIP. We like LWIP. It's kind of fully complete, has IPv6 support, has IPv4 support. But where we think there's a lot of opportunity for improvement is in how you manage the wireless side of these stacks. And that also ties into a lot of the problems we see on these microcontrollers, where the wireless portions of those stacks are precompiled binaries that are completely opaque to the user. And so it's our goal to make those wireless stacks completely open. So in terms of context, and this is the community-driven pitch, I'll jump over it because I know people talk about it a little too much. But just a quick note on where we chose to build this effort. We chose to build it in the Apache Software Foundation. So for those of you who don't know what the Apache Software Foundation is, it's the foundation behind a lot of the web infrastructure that came out. So it started in 1994. Jeff can correct me there if I missed it, but was officially incorporated in 1999. And the idea was, at the time, everybody was building their own web server. And so wouldn't it be better for interoperability on the internet if there was a common open source web server? And so that became the Apache web server, which is the #1 web server that everybody runs. Based upon the principles of the developers who did that, they decided to create a nonprofit foundation that helped other people run community-driven open source efforts. So what community-driven means is that it's meritocratic, and you don't have to pay anything to have control over the project. So it's completely free to contribute. You can come to our website, download our code, and submit patches. But the other side of that is it's also self-governing by the contributors. So no corporation owns the effort or has any control over the effort. It's the individuals who contribute to the project. So the way you become a contributor and the way you get a vote in the direction of our project is you submit patches. If you submit patches, you will become a committer. And if you're a committer, you vote on the strategic decisions in the project, and your vote counts just as much as my vote or any of the other committers' votes. And so it's really the idea is a project of individuals and contributors. And you look at some of the largest pieces of infrastructure, Hadoop, most of the big data stuff, the Apache web server, they've all been built this way. And the reason that this works is it's not a temporary alliance of people. It's individual contributors who are passionate about the project who carry it forward. So I'm going to now just kind of talk a little bit. By the way, feel free to interrupt if you have questions or comments. But I'm going to talk a little bit about some of the features of the Apache MyNewt system. This is by far not maybe our major feature, but it is something that underpins everything else we've developed. So I'm going to go a little bit more into it. So kind of the main part about Newt that ties everything together is we built our own build and package management system. So very similar to Yada that was in Embed for a while. Our thought is if you're going to go and develop and manage these large projects, you want to have a stable core operating system, and then you want to be able to redistribute third-party libraries and link them all together, and you want to be able to manage that. And that becomes very complex. So a typical use case for this was at Silver Spring Networks, where we had meters, streetlights, about 20, 30 different hardware SKUs, but we had a unified operating system that we had built, and you see this with a lot of people. We wanted to maintain our code base in parallel, but have customizations for each of the different products we developed. So we wanted to have slightly different things for the streetlights than we did for the meters. And so what we'd have is a core operating system component, and then individual code bases based upon that. And so Newt allows you to do that, and it allows you to compose your operating system, picking only the pieces you want for a given project, but still maintaining separate code bases. And the other thing that Newt does for us is, so that's the package management side. We've then tied build into that, so that when you take your development environment and you go to production, you can use the same tool to do both of those. So as an example, if you compile your operating system and you compile your application with Newt, you can then take that same code base that you could load it on a debugger, and you can automatically create a flash image for that, and you can automatically create firmware upload images. So it's the same build tool that takes you from debug to production. The build tool automatically signs images for you. It also maintains all of the symbol information and all of the Git history for every build that you have. So you have the entire history of that product through build artifacts, as well as debug and production versions. So when you go and you upgrade images in the field, all of that's automatically saved for you. So the idea is to help you maintain large code bases and to help you to move from debug to production in one seamless way. A few other highlights. Oh, all right. So one of the core elements of the operating system that we've developed is cross-platform support. We have spent an inordinate amount of time on this. We really wish that it was not the job of the operating system and it was outsourced a little bit. But how do you come up with a very good how that you can implement reliably across platforms? And how do you do that in a way that's very efficient for product developers, right? So how do you abstract a SPI interface? You don't want it to be too high level. You want to be able to run it. How do you abstract a UART interface? Do you use DMA? How does DMA look different across all of these platforms? So we've done a lot of work in really getting a how that's both efficient and portable across multiple platforms. We've also focused on the build and package management system here, which ties into how we lay out code. So as an example, on every build that we create, there's both an application. The two targets in the build are the application and the board support package. The build and package management tool itself understands dependencies. So the board support package typically relies on an MCUS support package, which is a full implementation of the how for that board support package. We've built in capabilities and all of that so that we can really develop a system that works across platforms. And then, of course, there's all the little details that we don't handle, right? Like ADCs and other things where we just give direct access to the chip. So we've kind of made a bunch of trade-offs there. Software upgrade, I've talked a little bit about. Debugging is another area where we've really focused. And then power management. So those are kind of some of the key areas for the operating system and where we've really put in a lot of thought to getting these APIs tied down right. To dig a little deeper into one of them, so just to take security as an example of one of the areas where we thought. So we've gone all the way through the product lifecycle, starting from provisioning. So as an example, most chips that you'll look in the ARM-based world will have, or probably Intel as well, they have some unique identifier that comes from silicon. If not, in order to do device provisioning within a manufacturing environment, you need to have a unique identifier for that device so that when you develop a management system in the cloud, you can actually come and understand what that device is doing. So we have APIs in our board support packages and in our MCU support packages that actually that allow you to hook into the silicon's unique ability to provide you a unique ID. We support generating a private key from that information and passing the public component out to a manufacturing station so that when a device comes and tries to get on the network, all of that is tied together. And that's built into the APIs we've built because provisioning is key to pretty much anybody who's developing an IoT connected product. In terms of upgrade, the bootloader does not have an unsecure option. So every image that you download to a device is secure. It just uses a development key when you're generating the image. So if you use Newt to manage your product, you are already using a secure bootloader. There's no secure bootloader option. In terms of communication, we support all of the communication security protocols. So we have DTLS support, but we also support all of Bluetooth security from a communication perspective. The RBAC there is aspirational. I'll call that out. We definitely believe in having role-based access control security for all of our management. That has not been integrated yet. And then data and tamper. One of the things that's always a pain, early on, nobody encrypts data on flash. And then when you go and you actually deploy a product and you start to have to sell to government or you start to have privacy concerns, almost everybody wants to encrypt data on flash. And so we have options in our flash file system as well as our circular buffering mechanisms and config mechanisms to support encrypted storage of data. And that's all built into the system for you. So if you start out and you don't want to use it, and then you want to switch to it, it's a seamless transition. And then we are TPM and smart card aware. So if we want to come up and validate some data or we want to sign, that's all abstracted. From a connectivity layer, Apache MyNewt has kind of, we've made some, so I'll caveat this with Runtime's view, because roadmaps are really, they're about the community. I can't speak for the Apache MyNewt project, but I can speak for what Runtime is working on in Apache MyNewt. And the two transports we started with were Bluetooth and Wi-Fi. We think there's going to be a lot of transports, and wireless transports are going to dictate IoT deployments. But we started with Bluetooth and Wi-Fi because they were standards, and they had interoperability processes around them that were way more robust than anything else we saw. So when you look at Bluetooth, it truly is interoperable across chip vendors, and the same applies to Wi-Fi. Whereas if you look at some of the low-power wide area standards that are out there today, you don't really have that interoperability framework there. So while we think they're going to be really interesting and exciting, we didn't focus on them first. So on Bluetooth, we support both a host and a controller. So we go down, we completely, so the first chip we supported was the Nordic NRF52. We completely replaced the soft device on that chip and provide all of the functionality that you would get with the soft device, but we do that in a portable fashion. So you can easily move from a Nordic chipset to a NXP chipset, as an example. And when you move, none of your APIs have to change, and you don't have to re-implement your Bluetooth stack. You don't have to re-implement your software upgrade mechanisms. All of that comes in MyNewt. And so we support all the way up there. On top of GAT, we currently run OIC. So the idea is to run, we run OIC natively on top of basically CoAP on top of GAT with OIC on top of that, and we provide our management protocol using OIC. We chose OIC because it was a standard protocol and it was surprisingly sane, JSON encoded data or CBOR, and it allows you to have the same framework for both management and application communication. So we really like that about it. We also support Wi-Fi support. The first chipset we support is the Wink 1500, but we're continuing to evolve our support beyond there. And that really is where we're targeting on our 1.0 at. So right now, the last release we had was 0.9. We are mid to end of October, we are launching with our 1.0 release. When you look at that kind of release, what that means to us is full Wi-Fi support, API stability, and we've already been running MyNewt in production with customers for about 6 months now. So we've actually, all of the operating systems are fairly nascent in this space, but we feel pretty confident given that we've had 6 months of production on the operating system and a whole bunch of API testing that it will work pretty well. Beyond that, we are committed to supporting Bluetooth. We think I think most people up here really like Bluetooth. We really like Bluetooth too. We are going to support Bluetooth 5.0. 5.0 really, what's exciting to me about 5.0 is the fact that, so the challenge with Bluetooth today is the small packet sizes. Specifically, both in connections, so it's 27 bytes in a connection, but specifically advertising packets, which are essential to developing a mesh. So when you have small advertising packets, 23 byte packets, you can't actually broadcast out routing information or anything without having a connection to a device. With Bluetooth 5, advertising packets are moving from 23 or 27 bytes all the way up to 290 bytes, which then allows you to really run mesh on top of Bluetooth 5. So we're really excited about Bluetooth 5. We plan on supporting a lot of the low-power wide area standards. So LoRa is one of them, but we're looking at also other sub-gigahertz mesh technologies, and we think that's an area where good wireless stack support can really help unlock it. And then there's, of course, all of the new 3GPP stuff. I think most notably there is NB-IoT, which a lot of the cell carriers are starting to deploy. And NB-IoT is essentially, for those who don't know it, it's LoRa in licensed spectrum. And a lot of the problems with LoRa in real deployments is that, it's great to have a star architecture for battery-powered devices because you can transmit really far and they know what channel to be on. But if you do that in an unlicensed spectrum, there's a very high noise floor. So as you have other deployments around you, sub-gigahertz doesn't work as well for them, whereas a mesh architecture works a lot better in unlicensed. So having NB-IoT in licensed, we think, is a really interesting technology because it'll be great for things like battery-powered devices that need long areas to go over. So just a few highlights from the networking stack. So I think the first stack, if you're going to go and look at our effort and want to judge the code, I think the first stack to look at is our Bluetooth networking stack. We've had pretty good performance results with it. So we support both central and peripheral modes for Bluetooth. We also support up to 32 simultaneous connections. And this is really an area where having good wireless stack support unlocks new applications. So the first people to adopt our OS when it was barely working and constantly changing were lock people, right? So when you're developing smart locks, what you want to do is you want to be able to scan for phones that are coming near a door, right? You want to be able to see those phones and see whether they're near enough to you that you should unlock the door and whether they're a phone you care about. The Nordic stack that was shipped, I think, was 3 connections in central mode and 1 connection in peripheral mode, which meant that you were severely limited in how many devices you could connect to. This wasn't because Nordic was bad at writing drivers, it was because they shipped a precompiled binary that had to work for all of their users, right? So you couldn't just, if you made 32 connections, you'd have to use all of that memory. And somebody who's developing a small peripheral doesn't care about having to go and connect to 30 devices, but somebody who's connecting to a lock really does care. And so having an open source option there allows people to then go and support more connections. We also support combined host and controller, as well as host-only and controller-only mode. So another very common place we're used is in BlueZ. Actually, the Intel folks went and ported MyNewt to support a controller-only implementation. And so we're run frequently with the BlueZ networking stack. And then just a kind of another thing there is because our stack is configurable, it's about 40% less code than the soft device when you run it in peripheral-only mode, because we don't need the central roles, and we don't need to enable all of this functionality. So it gives you fine-grained control over what features you run on the device. We've recently gone ahead and then added Wi-Fi support to MyNewt. So this is using LWIP and then the underlying wireless support. We have an abstracted interface to Wi-Fi supplicants. Currently it's with the Wink 1500. We're looking to add additional support. I think Runtime, we're pretty excited about Broadcom's chips, and then some of the MediaTek stuff that is combo, so both Bluetooth and Wi-Fi. But the idea is to abstract all of the supplicant interfaces. This is if people here are more familiar with Linux, there's a lot more modes, so the supplicant can actually be soft. In most of the MCU environments, the supplicant comes in a vendor SDK that's on a separate chipset, so you don't actually have to implement a full supplicant. We've integrated LWIP there, and we're looking at others. In terms of hardware support, these were the first 3 platforms that we really decided to develop our operating system. So the first use case we looked at was really developing it for the Nordic NRF 51 and 52, right? And at least in my mind, and I think other people's mind, it was really, how do we develop an open source soft device replacement, right? Because the real business value of taking this operating system, when you start to talk to people kind of outside of the engineering world, is that you can now have a single operating system that can run on multiple chipsets, and you can really then look at price performance between the various chip vendors in terms of the operating system. And so our thought was, let's develop a real kind of replacement for the soft device, and so we targeted the Nordic platform to do that. But at the same time, when you're developing an operating system, you really need to support multiple platforms in order to make things like your HAL work cleanly, right? Because if we had just supported Nordic, we would never have seen all of the intricacies of the ADC on the STM and Arduino, or on the Atmel platforms. So we supported those 3 platforms. We've seen a lot of usage on the STMicro platforms. They're very popular for Wi-Fi. They also are a very popular chip to go and do DSP offload on them. So we see a lot of people who use the Nordic chip as a host processor, and then when they have to do some sort of DSP or data processing, they'll wake up an STMicro chip. And then the Atmel SAMD, SAM-L21s are very popular on maker platforms. The SAM-L21s have fantastic low power support. So these are the first 3 platforms we supported. Post 1.0, we're really going to spend a lot more effort broadening this out. When your HAL and your driver interfaces and your VSPs are frequently changing, supporting a lot of platforms is very difficult. Now that with our 1.0 release, we're targeting API stability. Once we have API stability of the core, that's when we're going to really kind of expand and spend a lot of effort expanding this support. So kind of post 1.0, a lot of our efforts are going to be focused on improving the IP support that's in there and improving the number of platforms we support. So kind of that's the next 6 to 12 months is really rounding out platform support. But at launch, we support all of these. We support the full set of HAL, drivers, IP stack, Bluetooth stack on all of these platforms, software upgrade, bootloaders. It's all available. And I guess I'm running short on time, but for more information, MyNewt.apache.org. Come talk to me and say hi. You're welcome to join the development list. We're looking for contributors. Everybody's welcome. If the roadmap I presented here doesn't appeal to you and you want to add something, just join the dev list and we're more than happy to take contributions and add people to the project. So we're really kind of open. And that's it. Thank you very much.